my recollection, aside from the setup, which there's two spheres that are connected to something that looks like this, right? If my thoughts are right. So let me get this drawn, something like that. All right, so it looks something like this, and you're having to spin it, so these swing out at an angle theta. This is L, and let me see, you probably were asked to find a relationship between omega and theta, and then what else? The energy of the system as it swings. Is that it? Those are I think the only two questions I really have for this one. So let's start with the first question, which is find a relationship between theta and omega. In this case, theta represents the angle of the weights as it spins, and omega is the angular speed of the weights as they kind of spin around this axis. I'm going to start with a force diagram because I think this is the only way that this can be solved is by using forces. There are two forces that act on either of the spheres. We're going to look at one sphere. So I know that there'll be a downward force due to gravity, and then there will be a tension force because it's connected to that rod. And I think the tension force is going to be larger than the gravitational force because the tension force also has to cause the sphere to travel in the circle. There's absolutely no reason to expect that you guys shouldn't be able to do this. Right, this is right within our wheelhouse to do this kind of stuff first semester. There's not a whole lot here. You will have to break the tension up into component forces. So I would choose probably a coordinate system that looks maybe something like that. And something like this. From here, this is theta, and we'll have tension in the y direction and tension in the x direction, something like that. And those are both based on theta, so I'll have this one is t cosine theta, this one is t sine theta. Any questions about where those came from? All right. Net force in the y direction equals 0. So t cosine theta minus mg equals 0. So t cosine theta equals mg. How's that? Any troubles? All right. Net force in the x direction equals MAC. It's traveling in a circle. So T sine theta equals M omega squared R. Any questions about that? Okay. Just remember, when I ask questions like that, I'm saying, all right, no questions about this, so I don't know what the trouble with the problem is. Moreover, I'm saying if no trouble with this, then it's fair game for your test. All right? So I'm just going to do a little dividing here, and I'll divide the left side and the right side. I could do it this way if you're okay with it, but if you wanted to see it explained differently, I can, but I'm just going to divide. And that means that the left side will be sine over cosine, because the t's will cancel out. And the right side, the m's will cancel out, and I'll get omega squared r over g. This is pretty close to having omega in terms of theta, because the left side is going to be tangent theta equals omega squared r over g. In fact, I can multiply both sides by g here and get g tangent theta equals omega squared times r. All good? Well, the problem is r. R can't be in the answer. So I need to write something else in place of r. I'm allowed to have L in my answer. I'm allowed to have theta, of course, in my answer. So I think I'm gonna have to write r, which is this distance, because that's the radius of curvature. I have to write r in terms of theta. So that's just another triangle there. So I see that r equals L sine theta. So let's just take this over here, and I'll have g tan theta equals omega squared L sine theta. Kind of wish I hadn't made tangent theta. Wish I had left it as sine over cosine, because the sines would cancel. So I'm going to regress a little bit and write g sine theta over cosine theta. And that way the sine thetas cancel. So g divided by cosine theta equals omega squared times L. So you need to define a relationship between theta and omega. This is a relationship between theta and omega. All right? Yippers.
So the relationship can just be an equation, you don't need an explanation, right?
That is a relationship. Relationship is an equation. Any questions about that? Yeah.
Where did you get the mw squared r?
Centripetal acceleration can be written two different ways. One of those is v squared over r. The other one is omega squared times r. The m just comes from ma, right? Net force equals ma.
Yeah.
But for something traveling in a circle, it doesn't have a change in speed, it has a change in direction. So those are the two ways we learn to write centripetal acceleration. That okay?
Yeah.
All right, so I think question number 2 was to find an expression for the kinetic energy in terms of theta, probably. It's already in terms of omega by the start. We have to decide whether it's all going to be in terms of omega or it's all going to be in terms of theta. Well, I'll have to make that decision. It doesn't make any difference to me. We have a relationship here between theta and omega. When it's spinning, though, we should probably consider the types of energies that it has. I think it has two forms of energy when it's spinning. I think it has rotational kinetic energy. And if you don't like that, you could write the individual balls as having just regular kinetic energy. You'll have to pick. There's reasons to use one versus the other. So you'll have to choose, but it's only one of these because they're not changing location. So either you think of the balls as having kinetic energy because they're going in a circle, or you think of this as one object that has rotational kinetic energy. You'll need to pick one of those ideas. You're going to get the same answer, but you'll have to pick. But also, the balls have been lifted up a distance because they're swinging upwards. So the balls also have gravitational potential energy. So how would you like to do this? Would you like to do this in terms of the rotational kinetic energy or the translational kinetic energy? You'll have to pick one.
Translation.
Okay. So if we do it in terms of the translational kinetic energy, we use 1/2 mv squared, but we don't have v, we have omega. So we'll probably have to replace v with omega times r. So our total energy will be mgh plus 1/2 m omega times r squared. We have stuff to put in for all of these things. H might be the one you don't remember because it's been a long time since we talked about H, but we would probably have to write H in terms of, I'm running out of places to write this, but just zoom in here. This is H. And do you remember how we wrote that last semester in terms of L and theta? That's a solid no all around, huh? It's too bad. It's gonna make this hard on you guys. You guys gotta start remembering things. Do you remember how we did this? If you say yes, then I assume you can do it. If you say no, then we probably should have a refresher. It's up to you. Yeah?
I don't.
Okay, thank you. So, whole lot of stuff to put together here all at once. So let's work on it. M G L times 1 minus cosine theta. That's that part. Plus 1/2 m. Well, omega squared is right there. So I'm going to put omega squared here. And I'm going to need to put r squared here. So let's find, here's omega. It's omega squared already, so it's g over L cosine theta. That's omega squared. And I just took that right from here. And somewhere on this paper, we have r. Somewhere. Oh, there it is. R is L sine theta, so R L sine theta. I mean, there's nothing pleasant about this, but that's what the answer looks like. This is the kinetic energy in terms of theta. It'd be really hard to do it the other way, writing the kinetic energy in terms of omega, because you'd have like some kind of weird stuff with the sines and cosines. Yeah?
Why do you keep the R?
Oh, I shouldn't have kept the R, sorry. It's just L sine theta. Now this can be cleaned up some, and there's no reason not to. If you square the L, you'll get to cancel one of them. If you square the sine theta, you don't really gain anything, but you can. So you could clean this up a little bit, but it's just going to look messy no matter what you do. I do want to clean it up a little bit so you see something. MGL times 1 minus cosine theta plus 1/2 M L squared sine squared theta times G over L cosine theta. You guys are aware that when you write sine squared, you put the 2 there next to the thing, right? Somebody asked me about that last week, so. All right. Do you see that one of the L's cancels? So MGL times 1 minus cosine theta. Just a lot of letter stuff, but one of the L's cancels. So I have a MGL again, all times sine squared theta over 2 cosine theta. Now, there's absolutely no reason for you to follow along with this if you don't want to. But you can factor out the MGL. And you get what? 1 minus cosine theta plus sine squared theta over 2 cosine theta. There's some stuff you can do with the math here to make this easier to read. There are things called trig identities. And those of you who are in pre-calc and are doing trig identities know that you could probably cause some simplification here if you find the right combination of trig identities. I'm not asking for that at all. In fact, I think we were done somewhere back here. But just pointing out that there's probably something that could be done there. All right. So number 4. It talks about a CD. I'm going to treat the CDs as disks. So the disk has a moment of inertia of 1/2 mr squared. So there's R. Moment of inertia 1/2 mr squared. And that's 1/2 times 0.05 kilograms times 0.15 squared. Well, don't know what this is, but I'm certain that with a little handy calculating device we could figure it out. 0.5 times.
Diameter, that's would be 0.15. It should be the
Oh, it's the diameter?
Yeah.
Even smaller. Alrighty. So 0.075, even smaller. All right, so 0.5 times 0.05 times 0.075 squared. Wow, that's small. All right, 1.41 times 10 to the 1, 2, 3, 4, negative 4 kilogram meters squared. All right. So they want the kinetic energy when it's rolling at 1 meter per second. So the kinetic energy equals 1/2 I omega squared, and our velocity is 1 meter per second. So we have rotational kinetic energy, and we're going to have translational kinetic energy. Now, we found the moment of inertia we could plug in here. I'm just going to combine these, though. I think that's a more straightforward way to do it. I want you to get used to doing that. So I'm going to write this as 1/2 times 1/2 mr squared times v over r squared plus 1/2 mv squared. And we've done this a couple of times already. So this adds up to be 3/4 mv squared. And this is a lot easier to do than doing the two separate parts. So 3/4 times m, which is 0.05 times 1 squared. And this will be in joules, so 0.05. I get 0.0375 joules. Not terrible. All right. All right. So a single, this is number 9. So a single blade, they say, is 15 meters long, 16 meters long, and 150 kilograms. And there are 3 of them. I'm getting the impression they're going to be spun about their center. So let's get 3 of them. And do you mind? Thank you. That look okay? It's not great, but it'll have to do. One blade has a moment of inertia of 1/12 ml squared, and there are 3 of them. So I'm just going to multiply by 3. They're all being spun about the center, so that seems like a good place to go. So I'm going to kind of just set this aside because the picture is just to give me that. Maybe. But that's going to be I equals 3 times 1/12 times 150 times 16 squared. 3 times a 12th is 3/4, I think, right? So 0.75 times 150 times 16 times 16.
It'd be 1/4, wouldn't it? 3 times 12.
Okay, 1/4. So 0.25 times 150. 0.25 times 150 times 16 squared. Wow. 9600 kilograms meters squared. Now, it has you finding the kinetic energy at 2 different RPMs. So I'm going to call on 2 of you to tell me the RPMs in radians per second to make sure you're paying attention. So I assume you all did it, so it shouldn't be hard for you to tell me. I want 200 RPM in radians per second and 600 RPM in radians per second. I'll give you 60 seconds before I randomly call. I'm expecting this to maybe be 62 point something. All right. Now, from here, all you are expected to do is find the kinetic energy at 200 RPM and the kinetic energy at 600 RPM. You already have I, so it's just 1/2 I omega squared. Now, the last one, I'm more interested in how you did that one. So you were given this from its highest spin, so we're starting at the 60. It takes 5 minutes to come to rest. What is the frictional torque that acts on the motor? There's 2 different ways you could have solved this, and if you solved it at all. Based on what I just saw, many of you did not solve this problem because you didn't convert anything to radians per second. And I'm not saying all of you, but definitely a bunch of you. Now look, we're going to test your capabilities tomorrow. So, probably just a quiz, first few minutes class. So this is the stuff I'm going to ask you to be able to do. You could have used a motion equation. And found the acceleration. To find the acceleration, net torque equals I alpha. The torque acting is the torque due to friction. So that's probably the most direct way. You could have also considered this an impulse problem, but I doubt that that's probably where you went. But you could have impulse, which is net torque times time, equals change in momentum. But we haven't talked about angular momentum here. So I doubt this is what you would have done. I think this is what you would have done. But you need to find alpha. And it's just 62.83, final velocity 0, in 5 minutes. But you'll need to convert that to seconds. So 300 seconds. It's all for alpha. You already have the moment of inertia. So find alpha, plug it in there. That's going to be the net torque. It is negative. It's slowing the system down. All right. Whether we're doing a ring, a disc, a hollow sphere, it doesn't matter. The work you'll have to do is the same. So let's, for the time being, say that it is moment of inertia I, and towards the middle of this problem, we'll sub in one of the moments of inertia. Is that okay? So I want to start with the forces that act on the object. There are 3. There's normal force. There's gravity. And there's friction. It's rolling down the ramp, they said. This is the direction of the frictional torque. Before I go any further, you have to decide where you want the pivot to be. Do you want to treat the pivot point as the center of this rolling object, or do you want to treat the pivot point as the point that is at rest with respect to the ramp. I don't care. The problem is not different to me in either of those cases, but it might be different to you. So you asked, so do you want to do center or the point of contact?
The point of contact.
Okay, if we use the point of contact, because we are looking at a pivot point here, then it is the weight that is causing a torque, because it is the only force that is acting away from the pivot in a direction where it can cause a torque. And that means the frictional force is there to hold that point in place. Now, the only thing about using the point on the edge that causes you to probably be a little concerned is that you'll have to use the parallel axis theorem. Because we are not rotating about the center of the object, we are rotating about the edge. So we're shifting it one radius. Okay? So now let's talk about net torque equals I alpha. And for this problem, there's only one torque. It is the torque from gravity. And that's going to be a torque arm length times a force times the sine of the angle upon which it acts. Looking at that picture there, the torque arm is actually that green arrow. And this angle will be the angle of the ramp. So our torque will be R times mg times the sine of the angle of the ramp. That has to be equal to I parallel times alpha. Now, we're trying to get the frictional force. This won't do it for us because I don't even see friction in the equation. So we're probably going to use something else. I would probably recognize that there is something else we can use. We can use net force too, because that equals MA. I don't care about the up and down forces. I care about the ones that are aligned with the ramp, and that's going to be mg sine theta minus friction equals MA. You'll have to combine these two to eliminate A and be left with friction. I think it'd be smart for you guys to recognize that if there is a limit to what you know, just ask. It's not going to frustrate me to go over it. All right. This picture kind of looked familiar to what we just saw on the other page. So if theta was 0, it'd hang straight down. If theta was anything else, then it would be somewhat lifted up. This part is H. That all good so far? All right, well, this is L, and this is L. All good? Well, I see a triangle here, something like that. Do you guys see that triangle? Well, in that triangle, this would be the adjacent side, and this would be the hypotenuse. Okay, as long as you can see that, then A must be equal to L cosine theta for that triangle. Is that good for you guys? Okay. A plus H equals L. Is that also okay for you guys? All right, it's just this length here. Is that okay? All right. So L cosine theta plus H equals L. So if I solve this for H, I get L minus L cosine theta, or L times 1 minus cosine theta. I know it's been a long time. I urge you to, I want to set the problem up by first recognizing that this is a force problem. I think it's clear it's a force problem because it's asking about an acceleration and a particular force. So those are kind of the clues that make this a force problem. We're trying to figure out the acceleration of the ball down the ramp, and then we're trying to figure out the size of the frictional force acting on the ball. So that makes it a force problem. Yes, there's a change in height. You could use energy, but I think that's the harder way to do this particular problem. I'm not sure it'll find a force for you. So I think we're going to do this in terms of forces. I think there are 3 forces that act on the object. There's the obvious ones like gravity. We can do that one. And of course, there's a normal force. I hope notice that I'm not drawing the forces all at the center anymore. You're going to need to start, when you know there's torque, you should be drawing the forces at the point of application, which is where the force acts on the object. On your next test, that is likely to be asked of you. The last force is the frictional force, and it is this way up the ramp. These are the forces that act on the object. Any questions about that? All right. Well, you asked, so this object spins. Do you want to make the pivot point at the center, or do you want the pivot point to be at the edge?
I was doing it at the center.
Okay, that's fine. In this problem, there might be an advantage to doing it at the center. The only difference is that when you put that pivot point at the edge, you change which of the 2 forces is causing a torque. Putting it at the center doesn't change the problem. It just changes a bit of the analysis. So we have the pivot point at the center. From there, we can build a net torque equation equals I alpha. All right. The good thing about having a pivot point at the center is that most of our moments of inertia are already referenced from the center. If we had moved the pivot point to the edge, then we'd have to use the parallel axis theorem to change the moment of inertia. That's really the only thing that we have to do different. But let's go ahead and work the problem with the pivot point being at the center. This is the frictional force, this is weight, and this is normal. I'll remind you too that a torque is R times F times the sine of an angle. So I see that there is a torque arm, which is probably this distance from the pivot point to the point of application of the friction. And that torque arm length is the radius of my object. Any question about that? All right. I think this is a right angle here. So when I assemble the torque, I'm going to have R as my torque arm distance times lowercase f, because it's friction that is causing this torque, times the sine of 90 degrees, and that equals I alpha. So my torque equation is RF equals I alpha. But I want the linear acceleration, not the angular acceleration. This object is rolling, so there's something else I have to do. And this is something I need to continually impress upon you. There's a lot more substitution that has to go on when we're dealing with these rolling problems than what we had to do first semester. So we have angular acceleration here. The problem asks for linear acceleration. So RF equals I times A over R. This gives me linear acceleration, not angular acceleration. So when we're looking at like how points might be distributed, that substitution probably matters. That's an important point. Assembling the torque, that matters. That's probably going to be an important point. And using Newton's second law, that probably matters too. These are probably where your points are coming from. You know, when we start talking about partial credit for stuff. I want to do one more thing. I want to divide by R on both sides and write this as I over R squared times A. I'm collecting the R's and putting them by the I on purpose because every single moment of inertia has an R squared in it, right? It's either mr squared, 1/2 mr squared, 2/5 mr squared, or 2/3 mr squared. So under this circumstance, no matter which I put in, I'm probably not going to need to worry about R. So if you're looking back at problem number 13, put in a ring here, put in a disk here. This will tell you an expression for the frictional force in terms of the acceleration. We have a hollow sphere. So because we have a hollow sphere, we would put in for I 2/3 mr squared divided by r squared times a. And I know that some of you, all these letters kind of makes you crazy, but it's just algebra. Take as many steps as you need. You look a little inconsistent when you make algebra mistakes because you're trying to skip steps. Just don't. But I'm seeing here I can cancel the r squareds. And that just leaves me with this equals 2/3 ma. I can't answer the question with this. The question wanted the acceleration and the friction. I have an expression that shows me the friction is based on how much acceleration I have, so I need something else. So in this problem, torque is not enough to solve this problem. Now, just so you know, if we had set the pivot point at the edge, we would have gotten the acceleration as an expression. It would have saved us a little bit of time. Not much time, because it wouldn't have told us the frictional force. This way tells us the frictional force easier. So there's no advantage. No matter whether you set the pivot point at the center or the pivot point at the edge, you're going to need to do all of the things we're about to do next. So here's what we have to do next. We need another relationship, something else that can help us, because we have two unknowns in this relationship. So the next relationship I would probably consider is net force equals ma. That probably will work too. These things work together. So there are two forces here. There's the component of the weight down the ramp and friction. I don't feel like drawing a whole coordinate system and breaking everything up into components. That was a first semester kind of thing. I'm hopeful that you know that there's a component of the weight down the ramp, and that is mg sine theta. I encouraged you to kind of, memorize that last semester. So I'm going to write net force as mg sine theta down the ramp. I'm making this way positive. And friction up the ramp. That good? Yep.
So I had trouble distinguishing, because those forces are acting on different parts of the ball, right? Because the
Mhm.
friction. So you
But-
can still put them in the same.
Yeah, because these two forces cause the center of mass to accelerate. Okay? First semester, we always put them at the center because we didn't talk about the fact that those forces could cause the object to roll. Now, all of our objects were boxes, so they couldn't roll, right? Now that we have objects that can roll, the forces still act on the center of mass, and they still cause a linear acceleration. But those forces acting away from the center of mass also cause an angular acceleration. And so we have both things happening at once now, but it doesn't stop the stuff we learned first semester from still working. It still works here. So net force, it's a law, so it has to work this way still. Does that make sense? Okay. Something to think about for you guys who are perhaps a little more thoughtful, you can get the box to roll. Most of you know that if you push a box wrong, you can probably get it to tip over. We could look at problems. We won't, because it's outside the scope of our class. But you can look at problems with, well, what happens when something is too top heavy? That's how they analyze like SUVs to see if they're actually safe to be on the road, based on where their center of mass is and how much force it takes to turn them. The force that turns them is acting at the tires, where the ground is, but their center of mass is above that, so they can pivot over their tires and roll over. The rollover speed and radius of curvature is something that you do as a Consumer Reports. They analyze the tip over potential of vehicles to see if they are a tip over risk. For years, there's been legal precedent that automobile manufacturers have made cars that are tip over risks. And there's been a couple of famous court cases involving cars that are clear tip over risks and shouldn't have been put on the roads. They're unsafe to drive because even at moderate speeds, they had the potential to tip over. This is just a straight net force problem, though. I can add these two things together. Right? They are still based on the same values. Friction is still friction. In this case, probably my most direct route is to eliminate friction first and get the acceleration. So if I add these two things together, that will eliminate friction and will give me the acceleration. So I'll get mg sine theta. F cancels out, and that equals ma plus 2/3 ma. Now, do you notice that the 2/3 here would just be a different number if this was a ring or a disk or a solid sphere? So if you wanted to redo this problem for the other shapes, like in problem number 13, you could start from here because all the work would be the same. Yep,
Wait, what do you mean it cancels out?
I'm adding these two equations together.
Wouldn't that go in place of the F? Oh, wait.
No, you guys never remember anything from first semester, so how about we just do it the good old-fashioned way that you keep doing in algebra. It takes a little bit longer. I am going to substitute. There, I substituted instead. Same math, just takes longer. What? Guys, we did this first semester. I don't know why we're having the question now, but if you don't like it, then do this. Do substitution. Tried and true, Algebra 1. Pick one of these things. There's multiple methods on how to do algebra. And I'm not here to tell you which one to do. I don't know which one your teacher taught you. Do you know what I just did here? Is the substitution okay? All right, so do that one then. I like adding the equations together. It's more efficient. But that's just me. Do what you think works best. There's other options. This is the one that you guys know. Then do this one. It's still going to be mg sine theta equals ma plus 2/3 ma. And because you were confused by that a minute ago, you might have missed what I said. But the 2/3 that's right here, let's track where that came from. That's here. That came from I. So you can stop at this moment and recognize that this relationship will be exactly the same for a disk or for a ring or for a solid sphere. You just put in that moment of inertia, the 2/3, the 1/2, the 2/5, the 1. It'll make doing those problems a little bit faster. But at the same time, if you can't do this, you should probably redo the work so that you can do it on your own without a net, without Mr. Shelton helping you out. All right. I'm just going to add those together, 2/3 and 1. Let's see, that'll be 3/3. That'll be 5/3 ma equals mg sine theta. So I can cancel the m's and say that a equals 3/5 g sine theta. Now, that's where you go to the problem and you find out what the information was. Let's see. I don't need the radius. I need the 400. I don't even need the 400 grams. If it rolls down a hill, 5 meters long, inclined 20 degrees. All right, so I just need the 20 degrees. So this will be 3/5 times 10 times sine 20 degrees. 0.6 times 10 times sine of 20 degrees. I get 2.1 meters per second squared. Not bad, pretty easy. If I want to find friction now, I'll probably substitute right there. That's where you'll need the mass. So find the frictional force. I'll get friction equals 2/3 times 0.4 kilograms times 2.1 meters per second squared. And I find the friction to be itty bitty 0.55 newtons. This is all the rolling shapes, except for maybe a thick ring or something like that. So I'm just gonna pick one. It's starting at height h, and it's rolling down a ramp, length L. But because it's height h, I'm just gonna use the h. Right? They don't give me an angle here. I don't need an angle. I could get the angle because they tell me that this is L. So I want to point out they've given you the angle. You may not see it that way, but they have. Because I have H and L, I know that the sine of the angle of this ramp, theta, has to be equal to H over L. So you should know that those parameters are related. And so if you're asked for one or you're given one, you should be able to get the others. So in this case, I do have that. But since I have H and I can use H in my answer, to me, the easiest way to do this problem is energy. So I'm not going to worry about doing acceleration and a motion equation. I'm going to do energy. I'm going to say that there's gravitational potential energy at the top of this ramp, and that's going to be converted to two kinds of kinetic energy at the bottom of the ramp. This is the most direct way. This problem has a clear change in height and is asking specifically about speed at the bottom. That's an energy question all the way. You could use forces. Forces is the hardest way to do this problem. We're told to do this for all of the different things, but that last question, place them in order from fastest to slowest and most energetic to least energetic, is a trick question. They all have the same amount of energy. They all started at the same height. And you are going to be easy to manipulate on this next test. I want to point this out. You don't pay attention enough to the details, which is why you're going to probably have a difficult time on the multiple choice, because these little details will make a lot of difference. So yeah, they all have the same mass. They all have the same amount of gravitational potential energy at the top, which means they will have the same amount of total energy at the bottom. They will not all be traveling the same speed. And that's the critical difference. Some of them will have more energy shifted to rotational than the others. So you need to pay attention to vocabulary, because if I ask which one has more rotational kinetic energy at the bottom, that's a different question than which one has more energy at the bottom. At the bottom, the one with the smallest moment of inertia will be going fastest, and the one with the largest moment of inertia will be going slowest. And although I'm not putting the names of these things up here on purpose, you're being asked to put those in order. Those are the four rolling things. And again, you don't have to have them memorized, but you should be able to figure out which thing goes with which one of these because of what our definition of moment of inertia is. It's about how much of the mass is located away from the axis of rotation. So whichever one has most of its mass located far away from the axis of rotation, that's got to be the one with the biggest moment of inertia. And whenever one has most of its mass concentrated towards the center, that's got to be the one with the smallest moment of inertia. You should be able to place the labels here. And if at this point you can't, that doesn't speak well for what's probably going to happen for you next. But this is hollow sphere. This is a ring. This is a solid sphere. And this is a disk. Again, you don't have to memorize them, but you should be able to put these in order. I'm only going to do this once. Which one do you want me to do? I don't know who asked. Oh, Sarah asked. Which one do you want to do? We've done all but one of these in class at least once. So I would just pick whatever one you want to do, and then you plug your stuff in. Or we do the whole thing in terms of I, but that gets kind of messy.
I'll do
Disk? All right. If we're going to do this in terms of a disk, then I'll remind you that at the bottom it's 1/2 mv squared. That's the translational kinetic energy. And 1/2 I omega squared. That is the rotational kinetic energy. This all has to be equal to mgh. Now we're looking for the velocity at the bottom. We want the linear speed at the bottom. So probably the thing I would encourage you to do first is realize that we have two different versions of speed here, angular speed and linear speed. The problem asked for the linear speed at the bottom. We are probably going to have to do a substitution in order to get the whole thing in terms of the linear speed. Not the first time we've done this, just another reminder that we're going to have to do this. So that's my first substitution. Now, it's at this point where if I just do a little bit of algebra, not a substitution, just a little bit of algebra, I hope you notice that with just a little bit of algebra, we can group together the I and the R squared, reminding you that every moment of inertia has an R squared in it. And the R squareds will cancel out here. So this right here is as far as you can go without putting I in before you want to actually start getting to an answer. So this is where you'd probably sub your I in so you can figure out the different velocities. You said disk, so 1/2 mv squared equals, plus, that's a plus sign, not an equal sign, plus 1/2 mr squared on top divided by r squared on the bottom times v squared equals mgh. Good so far? All right. R squareds cancel. No?
No. Why did you add the kinetic energy to 1/2 I? Like, where did the 1/2 I E over R squared come
I took this
from?
and subbed it in for omega.
Why are we adding 1/2 I? Isn't it just kinetic energy equals the gravitational potential?
No. There's two kinds of kinetic energy.
Okay.
So we have the kinetic energy because the center of mass is moving,
Okay.
and we have the kinetic energy because the object is spinning.
So the two types of kinetic energy added together.
Is the total kinetic energy of the object.
Oh, okay.
Good time in New York, right?
Yeah.
Good.
For sure.
Good, for sure. And now you pay the penalty when you come back. Yeah?
So whenever whenever they ask for the linear velocity, how do you tell it's not the rotation?
In this one, with respect to speeds at the bottom of the ramp, it doesn't really say. I think that they probably would have been nicer if they had said linear speed. I assume they wanted to know how fast it was going because they want us to compare fastest to slowest. But you could say that that was ambiguous. I don't think your test will be ambiguous. I think your test will state clearly linear or angular.
Thank
Okay,
you.
you're welcome. And one thing to know is that if it does want angular, then the radius will matter. You'll notice that the radius is always canceled out when we've been looking for linear. That seems to be true for most of the linear examples, and that will remain that way. But if they ask for an angular speed, then you're going to need the radius. The radius is going to be in your answer. Okay. I want to just write one more intermediate step. After getting rid of the r squared, do you see where that 1/2 ends up? No matter which one of these, this is the number we're talking about that's going to be there, right? So the 1/2, that amount of inertia shows up here at the very end. It's adding more inertia, making the actual linear speed less, because some of the energy that would have gone to the linear speed is now going to the angular speed. It's siphoning some of that off. So this is just 1/4, so the whole thing becomes 3/4 mv squared, which equals mgh. Again, we're interested in v, so cancel out the m's, and we get v squared equals 4/3 gh. So v is the square root of 4/3 gh. So you repeat this again for the ring and the the solid sphere, and the hollow sphere, and you'll get the 3 different velocities that go along with this, and you'll be able to pretty well easily see which one's traveling faster, which one's traveling slower at the bottom. But in this case, they all have the same energy because they all started at the same height. Okay? Now, you guys are easy to fool. If I wanted to fool you after doing this problem, the easiest way to fool you for you, is that all right, Sarah? Is that pretty good? Yeah. All right. Hmm?
So, does it have to
On your very next activity, like tomorrow, if I wanted to, I'm trying not to harp on it. You can fill out, you can do the math here to say which one of these has more energy. But what I want you to know is that you should be able to figure it out with a qualitative, descriptive discussion. The ring has a moment of inertia of mr squared. The solid sphere, moment of inertia 2/5 mr squared. The ring is clearly harder to turn than the solid sphere. If they are moving with the same velocity, then they have the same angular speed. But the ring took more energy to get to that speed than the solid sphere. So it must have more energy total. It'll go higher on the ramp. And again, you guys are smart people. mg sine theta down the ramp, friction up the ramp. If this is the positive direction, this has to equal ma. Now it's slowing down, but the friction is pushing it up the ramp. The ring, which arguably is harder to stop once it's spinning, will go higher up the ramp. It's probably experiencing more friction because this is the force pushing it up the ramp. We talked about that last week too. Yeah. But that's this question.
which one is gonna get there first?
No. No, we didn't talk timing at all, but because the one is going to go further and they started from the same speed, probably the one that's going to go further, because it started at the same speed, it's going to take longer to stop as well. Probably a smaller acceleration, so it takes more time to get it to stop. But we did not talk about time at all.